my screen. Oh, it's impossible. Why?
Because
Sorry. Let me take a little bit.
oh, Yasunari, you can share if you click on.
Yeah. But I have some trouble with my local situation.
No worries, no worries. Take your time.
Yeah. Sorry. Ah. Why isn't?
I think it's starting, but maybe it's a bit slow. It says started screen share, but it's black screen.
Yeah. I don't know why. Well, I don't understand why this doesn't work.
The screen
so
says that it started to share, but
yes. So
It should be okay.
Yeah. I mean, I thought it should be tomorrow, so I'm not really well prepared. I'm sorry about that. So maybe I just try to get in from my iPad. So the number of meeting is what? 99
991
849
3831.
3831. Okay. Okay.
And when you share, I think you have to click on the program which you want to share.
Yeah.
We see your iPad. Yeah.
So yeah. Then how can I maybe sorry. Really sorry.
No worries.
I have mute. Yes. So how can I come in?
Yeah.
Okay. Can I see this?
yes.
So I tried to talk about rational normal quintic curves on cubic fourfold, and this is joint work in progress with Manfred Lehn and Duco van Straten. So I start from rational normal quintic. This is really a basic thing. And of course, this is fifth Veronese embedding of P1 into P5, and that is defined by this map. And let me denote it by C. And I want to calculate the normal boundary of that. So yeah. So it's it comes with of course we have Euler sequence of ambient P5. and on P1 we have yeah, this is on P1, this is all P1 5 6 and TP1. So the normal bundle is sorry, co-kernel there. So the normal bundle of C on P5 is the co-kernel of this map. And this is the map itself is Jacobian of this parameterization V here. So it turns out that this is just OP1 of 7 6 times. No, 4 times, sorry. So degree 28 and rank equals to 4. Yes. Then I put this rational normal quintic curve on a cubic fourfold and consider the moduli space of the curves on Y with Hilbert polynomial 5n plus 1. And I mean, of course, this Hilbert scheme has several components, and I pick a irreducible component that contains the rational normal quintic curve. Then I want to calculate the normal bundle of the curve inside of Y to calculate the dimension of this component and so on. So because I was I came late, so I omit the detail. But basically this was all P174, and this is normal bundle of Y inside of P5. This is basically OY 3, yeah. So if it is restricted to quintic curve, this gets 5, I think. No, 15. Yeah, 5 times 3 is 15. So this thing is degree 13 and rank 3, and this splits, of course, splits into line bundles. And we can safely assume that these relations, and of course this maps to this line bundle. So this degree is bounded by 7 from above, and the sum of these three numbers is 13. So this implies A1 is at least -1. And then we conclude that H1 of the normal bundle is trivial, and H0 of the normal bundle is 16 dimensional. So around this point, this is smooth, and the dimension is just 16. Okay, so let me recall the construction of De Jong and Star of symplectic, I mean, generically symplectic two form on the moduli space. So we have this fundamental sequence of normal bundles, and we take wedge 2 of this sequence and twist by the normal bundle of Y, and then we get this. And I think actually this bundle is isomorphic to the conormal bundle of the curve C inside of Y, tensored with omega of C. I mean, this is degree consideration. I mean, this thing was OY 5, so minus 5. So the degree was minus 15, while the normal boundary was degree 13. So it is the difference is just minus 2. So that is that is omega c. So by taking a long exact sequence of this short exact sequence, and then by using
I'm
this
sorry.
isomorphic.
I'm sorry. Probably in the middle term, H2 is missing, right?
Yeah. Thank you. Here we need the wedge 2. Yes. This is what you mean, yeah?
Yeah. Exactly.
Thank you. So this thing is isomorphic to H0 of the normal bundle dual. And I mean, if you look at the article of De Jong and Starr, this is the the construction of their two form. I mean, this comes from Griffith's construction, but basically this is the local description of the two form. And because I mean, this was what was this? Wedge 2 of we can calculate this term, and from this we know that this is just isomorphism. So that means the two form corresponding to this linear map is just non-degenerate. So we have symplectic two form on this moduli space. Okay, but we are also interested in boundary behavior of the moduli space. So I mean that means we have to look at various degenerations of rational normal quintic curve, and I mean it turned out that one of the most important degeneration comes from the degeneration in terms of the span of the curve, a linear span of the curve. So we look at rational quintic curve, which spans P4, and I mean that is more or less the same thing as generic linear projection of rational normal quintic. I mean, I assume that the image is smooth. Yeah, and then normal bundle of this degenerate rational quintic curve is calculated like this. I mean, this is the same calculation as before. And using this, we also know that.
I'm sorry, and as before, H2 is missing, right?
Sorry?
And as before, H2 is missing in the middle term of the exact sequence, and I mean in.
Yeah. Sorry, here, yes. Thank you.
And also in the bottom line.
Yeah, here. Thank you very much. So what I was going to say is that we can calculate the normal bundle, splitting type of normal bundle inside of P5. So from this, we still know that the modular space is smooth at this point. And if you look at this sequence, I calculated it, but I think yes. So I mean, yeah, I think I mean I omit the calculation in detail, but basically I think this space is non-zero this time. This is 4-dimensional. I mean it is easy calculation to calculate the split. Yeah, it is actually easy. What was this? So this is minus 15. And so we get the number is minus, so which 2? So minus 12. No. So yeah, minus 3, minus 2, minus 2, 0, 0, 1 or something, if I was not mistaken. So basically from here, you get the 4-dimensional kernel. That means the two form corresponding to this map has 4-dimensional null space. And let me illustrate how one gets this 4-dimensional null space in terms of geometry. So let me continuously work on rational normal curve spanning P4. It can be obtained, for example, just by omitting this middle term and embed it into P4. So this gives such an example. And from this parameterization, you can easily see that, I mean, this means x0 is this is S5, by the way. And x1 is s to the power 4 times t and so on. And from this parameterization, you can easily see that the minors of this 2 by 3 matrix is in the homogeneous ideal of the rational curve C, meaning that this C sits on a cubic score embedded naturally embedded into P4. And if I denote the -1 curve on this cubic score by E, then it is easy to verify that this quintic curve is in the linear system of E plus 4F. F is the ruling of the cubic scroll. On the other hand, the hyperplane section is H. That is given by E plus 2F. Then we think of cubic fourfold here and cut the surface by this cubic equation. Then we get something of degree 9. But if this curve, the quintic curve C, sits inside of Y, then this curve C must be a component of this intersection curve of degree 9. So that means we get something of degree 4. And by this description of the curves in terms of divisors, we see that residual curve D is in this system. And it is really straightforward to check that this curve has degree 4 and genus 0. So this is a rational normal quadratic curve inside of P4. Yes, and in terms of equations, I mean, it is something like this. So we have determinantal equation of cubic scroll here. So in our case, we just add one row and take 2 by 2 minors. And this gives equation, homogeneous equation of the quadratic curve D. So after this said, we can reverse the argument. So we start from 3 by 3 symmetric determinant representation of rational normal quality curve. Then we take two linearly independent linear combinations of these rows or equivalently columns, like multiplying 3 by 2 matrix and numerical constant matrix from the right, and then it gives 3 by 2 matrix with linear entries. Then we can form a determinant equation as usual. Then we get P2 family of cubic scrolls, and from this construction, this cubic scroll containing the curve, this D is qualtic curve defined by this determinant equation. Then we have, of course, cubic fourfold in ambient P5. So if we intersect this cubic scroll parameterized by P2 with Y, then we get degenerate rational quintic curves as a residual curve of D. So this gives explicit construction of P2 family of degenerate rational quintic curves on Y. So all these sits in Y. And then we can summarize this construction. So we consider the moduli space of rational normal quality curves on Y. Then it is rationally P2 fibration. And we can do the same calculation as before to calculate the dimension of the Hilbert scheme. The component, this rational normal component of the Hilbert scheme, and this is 13 dimensional, and this is 15 dimensional, of course. And this is in M. So it turned out that locus of rational curves that spans only P4 forms a divisor inside of our rational normal component of the modular space. And moreover, we can look at the natural two form, de Jong star two form on this modular space. And it is straightforward to verify that this two form has one-dimensional kernel. So we can further divide by this null foliation to get some space of 12 dimension. And here the two form gets symplectic. So here the difference. Sorry, no, not this difference, but this was 16 dimensional. So here the difference is 4-dimensional, codimension 4. So that is the geometric meaning of the kernel of the generically symplectic two form. So from this picture, it is quite tempting to expect that there might be some kind of contraction or some rational map to some space, which contracts this divisor of degenerate curves. And actually, my collaborators worked on this problem in the case of twisted cubic curves. And they started from a rational normal component of the twisted cubic curve on cubic fourfold y. And then they explicitly construct some morphism to 8-dimensional projectively symplectic manifold. And later, Addington and Len verified that these points of this symplectic variety Z can be interpreted as a projection to this so-called Kuznetsov component in the semi-orthogonal decomposition of cubic fourfold. So what they observed is something like this. So we have a twisted cubic curve, and we take, I think, structure sheaf, and taking a mutation of this structure shift. So this gets inside of Kuznetsov component. This is a 2-Calabi-Yau category, and actually this contraction morphism, this morphism image of this morphism really corresponding to the isomorphism class of these objects. So this was the observation of Addington and Lane. And of course, I have to remark that there's a work of Bayer, Lajos, and McCree, Noah, Perry, and Stellari, I think. So all these people worked really hard to get the general construction of Bridgeland stability condition on this Kuznetsov component. And they claim that they construct moduli space of a Bridgeland stable object. And they prove that it is a symplectic projective manifold. So we already have, I mean, quite general, quite generalized construction of this modular space Z. However, I mean, in some sense, their approach deviates from the geometry of a cubic fourfold, because they pass everything to a conic bundle structure induced by the they choose a line on cubic fourfold, then blow it up, and then they get the conic bundle structure over P3, and they basically transport everything to P3, and then there they use the existence of Bridgeland stability condition and play on some twisted category on P3. So in doing that, we somehow, my feeling is that we somehow lose geometric control on cubic fourfold. So what we are aiming at is just staying on cubic fourfold and understand the situation in terms of classical geometry of curves or some stable sheaves on the cubic threefold. Sorry, cubic fourfold. Yes. Yes. But starting, of course, this is really good. All of them are good result. So we want to imitate some of the feature here. So let me summarize a little bit about the mutation business. So we take smooth projective variety with vanishing whose homology of structure shift vanishes, I mean higher homology, and take algebraic C scheme S, and we have this product construction, and take an object from this misprint, the derived category, bounded derived category. Then basically we take a relative home space here and take evaluation map, and then the exact distinguished triangle completing the evaluation map gives the left mutation of A with respect to the twisting sheaf or Y of M. And of course, by the very definition, we have this orthogonality condition. And using this, we have following easy lemma. So if we take some kinds of tensor product here, of course A and B, these are objects in the derived category, then we can move the mutation from one side to the other side with minus sign. And actually, moreover, we can take mutations in both sides. All these things are isomorphic. So this is easy homological algebra calculation. And I mean, this is a relative description of the Kuznetsov component of cubic fourfold. So we have these three consecutive twisted structure sheaves, and it's I think left, right. It is really hard for me to memorize, but also one component is the definition of Kuznetsov component. And of course, we by composing left mutations as many as you like, we get projection to the Kuznetsov component. And actually, these triangulated subcategory is all equivalent if M is at least 2. And for later use, I just defined the dual of this left mutation. Then the previous lemma gives these kinds of isomorphisms. So we can move this projection factor to the other side with minus signs. And also we can take both. All these three things are isomorphic. Okay, so let me explain, review about determined line bundle business. I mean, this is so-called Le Potier construction. So we start from—
I'll just make a quick announcement. Sorry, just a quick announcement. We're sort of finishing 20 minutes past the hour, just for everyone to know. So we will sort of end.
I'm really sorry about that.
No, that's not a problem. We will end at 11:20 GMT time now.
Okay, I'm sorry. Yes. So I want to construct determined line bundles on a modular space. So this is classical situation. So M, I mean, we fix numerical element of the K group of Y, the variety, smooth projective variety. and we consider the moduli space of stable sheaves on Y with whose K group class is nothing but C. And we can safely assume that we have inversor family on the product. Then we take subgroup of K group, which is perpendicular to C in the sense of this equality. So this is the tensor product is just a product of a Grothendieck ring. And if we take chi of that, then it's 0. And we need this condition because this universal family is just well defined up to twist of line bundles from the variety Y. Then Le Potier map is this thing, the lambda m. So whenever we take an element from this C top, we can form determinant line bundle on the modular space M. So this gives some line bundle on M. And actually, by the GIT construction of modular space, this modular space M is equipped with a natural ample line bundle of the form this form, and this A coming from some good subspace subgroup of the K group. Okay, so here we come to our hypothetical argument. So since we want to construct some analogy of this morphism in the case of rational normal quintic curve, so so we somehow assume that there's some morphism to other variety or perhaps rational map, and then inspired by the result of Addington and Lane, it is plausible that the target of that morphism should parameterize projected object in the Kuznetsov component. So where was that? Yeah. And but before getting into determinant line bundles, I need to remark that we have to pass to stable sheaves of Hilbert polynomial 5n plus 2 rather than considering the curve itself, because to get the reasonable moduli space in certain sense of the objects in the Kuznetsov component, and Kuznetsov component A is two Calabi-Yau category. So if we have some stable object, simple object from here, then this simple of x I of f prime behaves like sheaves on K3 surface. So if f prime is simple, then x2 0 and x2 is one-dimensional, and x1 of course corresponding to the tangent space of our virtual moduli space. And our component, our curves deforms in 16-dimensional family. So the Euler pairing of projected objects should have the number -14. And actually structure sheaf or ideal sheaf of the curve itself does not satisfy this equation. But if we twist a little bit, and consider stable sheaves of Hilbert polynomial 5n plus 2, then I mean basically Grothendieck-Riemann-Roch assures that this equality always holds. And of course, in this moduli space of stable sheaves, the typical element is just image of OP11 under the Veronese embedding. Okay, so from now on, we pass to stable sheaves, and we work on this moduli space. And we, as I said, we assume the existence of morphism to other variety, perhaps rational map, I don't know. But we loosely assume that the image of the point of the moduli space here corresponds to the object in Kuznetsov component. That pi m is the projection factor defined before. And moreover, I mean, this is a hypothetical argument, so we just assume that there is an ample line bundle on the target space of Lupotier style. That means Z, an ample line bundle should be of the form of this form, because I mean we assume that Z is the moduli space of projected object. So if you have a universal family of sheaves on M, then we take a relative projection and take test object, then form determinant line bundle. And we assume that an ample line bundle on Z can be written in this form. Then by just what we looked at in the previous slide, we can move this projection factor to the other side. Then this is just something given by Lupotier map, namely the value of Lupotier map of this projected test object. And so we are interested in this space, subspace of subgroup of Grothendieck group. So it is perpendicular to the numerical cross of the parameterized sheaf, and it is the image of pi dagger map. And it turns out that this condition is just orthogonality condition written here. So in this hypothetical situation, whenever we take some class from this lambda, we get a determinant line bundle on the target space. I mean, the pullback of the line bundle here. Okay, so then we consider that situation that cubic fourfold is very general. Then it contains no special surface, so the algebraic cycles is just generated by ample class over rational numbers. So the image of Chern class map is inside of this five-dimensional rational vector ring. But here we have these linear conditions. These are linear conditions in A. A is the variable, and C and O, OI, 1, and so on. These are constants. So we have 4 linear conditions inside of basically five-dimensional vector space. So the image of this lattice or I mean, subgroup lambda is just one-dimensional. So the numerical class of possible test object is unique up to scalar multiplication. And by playing with Riemann-Roch again, we can check that the class of that class. I mean, I denote this class by E of 5n plus 2, and the Chern class is of this form. And this is the primitive element in the numerical K group. Then we can more or less get the unique line bundle. Just plug this test object in here. And I mean, this coincide with the observation that we should get the projective symplectic manifold starting from the some modular space from cubic fourfold, because this projective symplectic manifold, the very general member of deformation of this is of just of Picard number 1. So I mean, this agrees with this hypothetical guess that we only have one choice of the line bundle, which should be given as a pullback from the symplectic manifold. So somehow by doing this, I mean, up to here, everything is hypothetical. But the definition of this line bundle L is perfectly fine, because this happens on this modular space, and this modular space, of course, has universal family and so on. So we really have this line bundle. Okay. Then let me explain what we got so far. So we started from looking at the general member of the rational normal component. So let us recall that this space, this is modular space of stable sheaves of Hilbert polynomial 5n plus 2, and I denote by my the irreducible component that the sheaf on rational normal quintic curve belongs to. So then the claim is the following. So first, if we take sheaf from this component, then H0 is two-dimensional and H1 is always 0. In particular, F is one regular. So this is first claim. And the second claim is that if F is generated by global sections, then Kuznetsov projection, the image of Kuznetsov projection, is just a shift of some coherent sheaf of rank 9. So here I take pi 3 was L minus 3, L minus 2, L minus 1, L0. So this is kind of unusual factor to look at, but yeah, just we just take this. I will explain a little bit why we do this. And of course, if our sheaf F is really generic, supported on rational normal quintic curve, then this G is a vector bundle. And here, I mean, the more somehow the most essential thing is the first claim, because by the vanishing of higher cohomology, we can easily calculate the projected object from the resolution of the sheaf on Y. For example, if our F is the push forward of O1 by fifth Veronese embedding, then it is really easy to verify that the resolution is of this form. And because I mean higher cohomology vanishes, basically what we have to do is just cut off this complex here. Yes, because we go up to -3. So in this case, G is just an image of this map. And of course, I mean, for example, the second, third claim is easy because I mean we can calculate the depth. I mean, F is stable sheaf supported on one-dimensional scheme, so this it's pure. So the depth is 1. So and by going into this direction, then the depth goes up. So 1, 2, 3, 4. So this has depth 4. That means G is already locally free sheaf. And if you degenerate the sheaf a little bit, then of course the type of projective resolution changes. But as long as the sheaf F is globally generated, the projected object is shift -3 of coherent sheaf of rank 9. And in a sense, this first point is important. And this comes from the another theorem. So here we work on P5 and take analogous moduli space of stable sheaves of Hilbert polynomial 5n plus 2, and then take the component the rational normal curve belongs to. Then take generic linear projection to P1, and we push forward this sheaf on this P1. Then we can show that this push forward sheaf always has this splitting type. I mean, there are several numerical possibilities of the splitting type, but we can somehow show that the push forward is always of this type, as long as the sheaf is in the rational normal component. And actually, this assumption, the sheaf is on the rational normal component, is really important because otherwise we cannot prove this theorem, and we need some kinds of case-by-case analysis of projected sheaf. And I mean, here we already have some trouble with non-irreducibility of the moduli space of stable sheaves. So we have intersection with other component, and there we have of course the tangent space. I mean that point is not smooth at that point because you have several components at that point, and yeah, we have big, I would say, great deal of trouble there. Yeah, and you may ask, what about the stability of this projected sheaf? And this is again related to the consideration of determinant line bundle. And I mean, by the result of Knudsen and Mumford, we take some perfect complex, which is proportional to the test object, which was numerically unique, as I explained. Then we take, I mean, this may not be L. This basically this can be some multiple of L. But choosing this object, we can canonically produce a rational section of this determinant line bundle. And if this complex here is quasi-isomorphic to a two-term complex of locally free sheaves, then this section theta E is just a regular section, because you have a linear map between locally free sheaves of the same rank. So if you take the determinant, then it gives a section of the difference of these two line bundles. And our observation is that we can construct a rational section of the line inverse of the line bundle L that is defined before at the generic point. And also we can construct a non-vanishing section of L to the power minus 28. So this may look funny, but somehow we can check that there's a rational section at the generic point of the degenerate locus divisor. While we cannot create any rational section of a positive power of L along D. So this is I must say numerical experiments on computer, and we have further trouble, and which is this. So the sheaf F may not be globally generated. So how can you get that kind of sheaf? It's easy, because if we have P1 to P3 and the image have a triple point, and these three, tangent directions span three-dimensional space, then we know that H0 of F is only two-dimensional. So these two sections cannot generate the stalk at this triple point. So in this case, F has a presentation of the form O2 plus O minus 1. Then absolutely the corresponding projected object is not a sheaf. So this means that we cannot, it is not the right thing to do to look at the moduli space of sheaves on Y. Then we realized that actually the sublocus of the divisor D is the critical locus. That means the locus of sheaves whose support, the linear span of the support is only three-dimensional. Yeah, here, this kind of curve can live on singular cubic surface, but we cannot produce this kind of singularity in P4. So this P3 condition, spanning P3 condition seems to be very critical. And we can observe it in a different way, namely numerically. So we take two rational curves. One thing is this degenerate divisor. So this was rational P2 fibration of some other moduli space. So we take fiber P2 and take a line. So this is gamma 1. And another curve is just take intersection with P3 inside of P5. Then we get smooth cubic surface. I mean, the Y was the cubic fourfold, and S is smooth cubic surface, and take two skew lines and look at this linear system. Then it is easy to verify that this is rational quintic curve. And this linear system form P4 family. So we take generic line from this P4 family. And everything is given in concrete way. So we can calculate the intersection number with our determinant line bundle. And the result is this. So if we take P1 from the fiber of this P2 fibration, the number is 0, while if we take something from surface, then it gets -3. So that means we have moduli space M and some divisor D. But we have a sublocus D3. And here, and the intersection with the determinant line bundle is really negative. So that suggests that we need some kinds of modification here. I mean, something like wall crossing phenomenon. Okay, so now we are concentrating on studying rational quintic curves on cubic surfaces. And then it turned out that this is really classical problem dating back to Max Noether, and also several papers in the literature like Katz and Corey and Weinsencher. But unfortunately, they only look at generic curve, smooth curves. But somehow, trouble is seems to be concentrated in non-normal surfaces. I mean, in terms of degeneration, not much degeneration that occurs on smooth surface, but if you pass to non-normal surface, you can create, various kinds of funny degenerations, which gives you something. I mean, the support has genus 2 or something like that. Then something funny can happen there. So, but here, the work, our work is really in progress. So I refrain from explaining too much, and I think this is the end of my time. So I just stop here. I'm sorry for being late.
Not a problem. Thank you very much. Thank you. Okay, so any questions? Okay, so if there are no questions, let's thank the speaker again. Thank you very much for the great talk.
Thank you.
Okay, so I'll just stop recording now.